In this video, we're going to see some models for recognizing handwritten digits. We're going to use the MNIST database, which is sort of like the Drosophila of machine learning. Everybody who studies machine learning has probably trained the model with the MNIST database. It's available on the web from this website that we're seeing here. There is 60,000 training examples of handwritten digits with their associated labels and 10,000 test examples. The model that we're going to look at is called LeNet. This is a convolutional neural network model from the 90s, which was one of the first commercially successful applications of neural networks, and it was used for reading numbers in checks in the United States. All of the code that I'm going to show you is available on the Knet tutorial page. So if you install Knet and look into its tutorial directory, you'll see all these notebooks, and we're going to look at two of these notebooks. So the first notebook I'm going to show you is for introducing the dataset. So I'm going to the first box loads the necessary packages. The second code box loads the actual data. And if we look at the length of the training and testing data, we see that it's 600 and 100. The reason for this is for training purposes, the data has been mini batched into chunks of 100 images each. So here is the first such mini batch with its dimensions. The input is 100 images that are each 28 by 28 in size, and the output, the desired output, is basically the labels for these images. So let's look at some of the images as an example. Let's see, these are the first 5 images from the test data set. These weren't used for training, and we can see that they're, easily recognize what digits they are. And here's the correct answers for them. 72104. We're using the hex digit A or 10 here to represent 0. So this is what our data looks like. Some handwritten digits, individual digits with their correct answers. And notebook number 5 is a implementation and explanation of the LeNet model for this data set. So I'm going to just show you the training curve. So there's a lot of introduction here, some experimental stuff. This is the model definition here. As you can see, the whole model is defined within a couple of boxes. And the LeNet model consists of basically 2 convolutional layers and 2 fully connected layers. Don't worry about it if you don't know what those things mean. So the only thing I'm going to do here is show you the actual results, the error results. This. Now at this point I have a chance to train this model from scratch, which takes about 400 seconds on my machine with a V100 GPU, but we also have a chance to just reload the last trained model we have. For comparison, this is just another model that we're going to load, and I'm just gonna give you the error plot. Okay, so let me explain a bit what this plot is. So the x-axis is the number of epochs. An epoch is basically one passage through the whole training data of 60,000 examples. So we do that 100 times. We go over all the examples 100 times. The y-axis shows the error rate, and there are 4 curves here. These 2 curves belong to a multi-layer perceptron, and these 2 curves belong to a convolutional neural network. This notebook basically argues that convolutional neural networks learn much faster and generalize much better when applied to image processing tasks. The reason there is 2 different curves here for the convolutional network, and one is for the training set of all the examples it's seen already during training, and the error rate for these is basically 0. The other one is for test examples that it's never seen before, and we can see that on examples it's never seen before, the error rate is about 0.5%. So we're basically getting 99.5 of these test examples correctly. Now if we look at the original MNIST page, and toward the bottom there's basically a table of all the different types of learning algorithms and their error rates listed on the right. So the record, I think, down here belongs to some convolutional nets that have been trained with distortions, which means they didn't only train them with the 60,000 examples, but they added their own examples by taking those and twisting them around and adding noise and distorting them, which basically had the effect of getting the model to generalize better. But even without doing that, we were able to get something close, about 99.5%, using the original LeNet.